Okay, what's up guys? This is for a student who asked me, how can I find the focus of a parabolic mirror? Okay, obviously, since it's called a parabolic mirror, we need a parabola. And if we're going to talk about parabolas, we need to use a particular equation. I realize that this is going beyond what we discussed during the class time that we had together, but that's only because a particular student was really motivated to be able to find this focus accurately, and I want to. It's my job to be there to support that kind of initiative, and I think that's good. It's cool. It's nice to be curious. The first thing you need to know is if we're talking about a parabola, let's define what a parabola is. I'm going to start by defining what a parabola is not. A parabola is not a circle. A circle is defined as, go ahead and say it with me. You guys are, Math 3, you should all be able to finish this sentence for me. A circle is the set of all points equal distant from a given point. Okay, cool. So here's that given point, and these points are all equally distant from that given point, and it looks like a lovely, beautiful circle. Okay, that's a circle. We're not doing circles. We did circles in 4th grade. Actually, that's not true. There's a lot to circles. Circles are awesome. Circles are a really cool part of conic sections, and every circle has its own equation. It can be located in all different quadrants of the graph, and you can have overlapping circles and sectors and chords and arcs and radians, and there's a lot to circles. I totally take that back. Circles are awesome. But parabolas are awesome as well, but they're not circles. And here's how they're different. Instead of saying all of the points that are an equal distance from one given point, which is the circle definition, instead I'm going to say all of the points that are the same distance from the focus, a focus. I'm going to say a point, and I'm going to call it the focus, and a line called the directrix. Okay, so one more time. A parabola is constructed of all of the points that are the same distance, exactly the same distance away from this point called the focus and this point called the directrix. Let me start with the first point. That might sound a little confusing at first, but let me start with the first point that qualifies for that argument. Remember, I said all the points that are the same distance from the focus and the directrix. Okay, so if I grabbed a ruler and I measured it out, I could say that this point right here, which we call the vertex, don't worry about that word right now, this point is some amount away from the focus. And just because I'm going to use the letter P, it's P away from that focus. Well, it also is P away from the directrix. Okay? So can you see what I mean now by saying that this point is the same distance from the focus? This point is the same distance from the focus and from the directrix. If you took your ruler out, P and P would be the same, right? Good. Let's find some more. How about that one? Whoa. Why did I just throw that one out there? Okay. At this point, I'm looking for points that are the same distance from the focus and the directrix. So I'm going to go ahead and grab my ruler because I believe in attending to precision, especially when we're discussing things that require a detailed approach. Okay, now this point right here, how long is that blue line? I don't know. You don't know either. It doesn't matter. The only thing that matters is that this blue line and this blue line are the same length. That's why I drew them in the same color. That's why I drew them both with a ruler, attempting to make them the same length as best I could with this piece of software. Okay, so this point qualifies as a member. It gets a pass into the VIP club of this parabola. This point counts as a member of this parabola because it is the same distance as it is from the focus to the directrix. Let me show you an example of a point that does not get into the club, that does not go past the velvet rope. How about that point right there? Okay, this point right here is a phony, is a loser, is a no-go, is a dude with a fake ID or something. You know, the bouncer is not going to allow this point in. This is not a member of the parabola. Why not? Because this distance from the focus and this distance from the directrix are significantly different. I'll say that just one more time really quickly and make sure that that sinks in, because if you get this, I won't harp on this anymore. This is the last time, but I need to check for your understanding. If you get this, you'll get the rest of it. This red dot that I just made here is not part of the parabola that I'm about to draw. The reason why is because its distance from the focus here and its distance from the vertex here are massively different. They're not the same. So it's not in the set of points that creates the parabola. That's as clearly as I think I can put it. If more clarification is required, please follow up with me via email, okay? Right. So now let's stick with the members of the club, okay? That one's a member. I'm gonna say this one's probably a member right over here as well. Same distance from the focus to the directrix, roughly, at least, okay? And I'm gonna say that maybe this one right here looks about right. And I'm gonna say that that one is, yeah, just let me visually confirm that. This distance here and this distance here, yeah, those look like about the same. Okay, everything is looking good so far. Now I'm going to make the bold move here of actually connecting those points together in a continuous curve that is not a circle, that is not an arch, but a unique shape. It's a form that we call, it's a type of conic section, meaning that if you had a cone and you grabbed a samurai sword and you sliced it, you could get one of these. If I took my samurai sword and I went like that, I could end up with a parabola. Now we'll talk more about samurai swords later. That's another cool math topic. Okay, so we've got what looks like kind of, I know you know what a parabola looks like. It looks like kind of half of a parabola. But the cool thing is I'm introducing the idea of how to deal with parabolas, right? I mean, kind of from the ground up. What is a focus? What is a directrix? What is the vertex? So that's why I've chosen a simple example where the parabola has the y-axis. The y-axis, right? This thing right here is the y-axis. The parabola has the y-axis as its axis of symmetry. And I know you guys are familiar with the concept of symmetry. So an axis is a term that generally refers in science to a vector or a line around which something spins. That can be applied here because if you took this y-axis and you pinched the top and you pinch the bottom and you spin it, you're going to get a really cool parabolic mirror. Yeah?